Hello again, and welcome to Advanced Physics for High School Students. This is Lesson 68, and it is entitled Heat Engines and the Carnot Cycle. Heat engines, especially internal combustion engines, run much of modern developed societies. Combine machines run by heat engines with machines that are run by electric motors, and I would venture to guess that you've accounted for more than 95% of the way that industrialized nations use energy. It's hard to imagine the United States without the automobile, and it's hard to imagine automobiles without engines. What's the physics behind them? More importantly, what's going to be asked about them on the AP Physics B exam? That's the subject of today's lesson. Let's begin with a technical distinction, though modern popular culture doesn't bother with it. Technically, an engine is a machine that converts thermal energy into mechanical energy, whereas a motor is a machine that converts electrical into mechanical energy. While you may hear your friends talk about the motors in their cars, the power plant of an automobile is actually a heat engine. Even the auto industry doesn't bother with the distinction. After all, General Motors manufactures a big fraction of the world's cars, specializing in the development and production of heat engines in nearly every one of them. I suppose the name General Engines just doesn't roll off the tongue in the same way. In case you didn't get that, you're supposed to laugh at that last point. Let's remind ourselves of the distinction between heat and work. You may recall heat consists of random energy, whereas work is directed energy. While it's possible to completely convert work into heat, it is not possible to completely convert heat into work. That's basically a statement of the second law of thermodynamics. The job of a heat engine is to harvest useful work from a source of heat. The more efficient the machine is, the more work you'll get out of it for every unit of heat that flows into it. The principle of conservation of energy allows us to represent energy flows graphically, such as in this diagram that's here. Thermal energy, QH, or Qn, flows into the heat engine from some source of energy, known as a hot reservoir, at a high temperature, TH. In the engine, some of this energy is converted into useful work, W, but the second law of thermodynamics precludes getting more than some upper limit out of it. After the engine has wrung as much useful energy out of the heat as it can, there's still some heat hanging around, and the cool heat, QC, or Q out in this diagram, passes out of the engine into what's known as the sink, or some cool reservoir at some temperature Tc. The diagram here represents this energy flow. Practically speaking, in a car engine, the hot reservoir or the source is the heat produced when the fuel burns inside the engine. It's in the hydrocarbon bonds in the fuel. The cool reservoir or the sink is the Earth's atmosphere, where the exhaust is dumped out the tailpipe. The principle of conservation of energy says that the energy in equals the energy out. In equation form, we can write this as QH is equal to W plus QC. We want to get the highest possible bang for our buck, and we measure this using a ratio called the efficiency, E, of the engine, where E, the efficiency, is the amount of useful work divided by the amount of heat that I have to pour into it. This equation can be written in many different ways, but I remember this one because it just makes sense to me based on the definition of efficiency. However, there's one other way to write it that's going to prove useful in what's coming. I can rewrite conservation of energy as work is equal to the hot heat minus the cold heat. If I then substitute that into the efficiency formula, then I can rewrite the efficiency formula in this way. And taking it one step further, so far there are three important equations we've written down. One consequence of this last relationship is that if you want the highest efficiency possible, then you ought to make the exhaust temperature as low as possible. Typical automobile engines have efficiency ratings of about 35%, which means most of your investment in gasoline ends up going out of the tailpipe of your car. Dr. Jack Taylor, my old Rhodes College physics professor, summed up the laws of thermodynamics in this way. He said, the first law says, you can never win, you can only break even. That's a statement of conservation of energy. The second law says you can only break even at absolute zero. That's a statement of this efficiency equation. An important corollary was that you can never get to absolute zero, therefore you can neither win nor break even. By all of this, he means that whenever you convert heat into work, you'll have to invest more energy into the conversion system than you'll get useful work out of the conversion system. Let's solve a numerical example at this point. An internal combustion engine operates with an efficiency of 18%. The engine produces 2100 watts of power on average while operating at peak performance. A. What is the rate of energy flow from the high temperature reservoir into the engine? And B. What's the rate of energy flow from the engine to the low temperature reservoir? I'm going to start, as I will start many of these problems, by sketching this diagram of the energy flow. I'm told that the engine produces 2100 watts of power. Now what that means is that the work that is coming out of the engine is 2,100 joules per second. So let me look at a time period of 1 second and look at the amount of energy that's going into this situation and the amount of energy that's coming out. The efficiency is 18% or 0.18, and that's defined as the work divided by the heat that's coming into the engine. So from that I can calculate what heat is flowing into the engine. I'm going to take the work and divide it by 0.18. I find that I have nearly 1200 watts of power flowing into the engine if I'm getting 2100 watts out. Now notice I'm calculating in terms of joules per second. If I just take 1 second as my time period, then a joule per second is going to be the same as watts. Now, what about the rate at which heat flows out of the reservoir? I can use conservation of energy to solve for that. So let me take the difference between the heat that's flowing in and the work that's coming out, and the rest of the heat is actually going into the cool reservoir. I find that I've got nearly 9600 watts that's going out the tailpipe. What I want you to see is that I have a tremendous investment in energy in order to get useful work out of this engine, and there is a tremendous amount of energy that is going wasted out the tailpipe. It may be that it's worth it for me to make that investment, but you should be aware that I still have a lot of energy that's going out in the form of heat when the job is being done. So now, what's the upper limit of the highest possible theoretical efficiency of a heat engine? Frenchman Sadi Carnot posed that question in the early 1800s, and his ideal engine is now known as a Carnot engine, which undergoes what's come to be called the Carnot Cycle. In what follows, I borrow extensively from the words of Dr. Michael Fowler, who's one of my old instructors at the University of Virginia in graduate school. At that time, this is the time of Carnot, the main power sources for industry were water wheels, but steam engines were just becoming efficient enough to begin replacing them. Not surprisingly, perhaps, Carnot visualized the heat engine as a kind of water wheel in which heat, or the fluid, dropped from a high temperature to a low temperature, losing potential energy, which the engine turned into work done, just like a water wheel. I'll show you a simulation of Carnot's engine with an accompanying PV diagram showing each of the steps in the process. For those of you interested in images, this is a colored engraving of Sadi Carnot, a young French engineer, and his machine is here. It's a piston that is showing a connection to a flywheel, and there's a PV diagram that's going to show the different processes, as well as a thermometer here on the left. And you can see what the different processes are if I start and let this run. Historically, Carnot thought that at the time heat was a fluid, which was an important principle in the caloric theory of Lavoisier. Remarkably, the naive potential energy of a caloric fluid approach gives exactly the right answer for the efficiency of an ideal engine. Carnot accepted that there was an absolute zero of temperature, from which he figured out that on being cooled to absolute zero, the caloric fluid would give up all of its heat energy. Therefore, if it falls to only halfway to absolute zero from its beginning temperature, it'll give up only half of its heat, and an engine taking in heat at temperature T and shedding it at temperature 1/2 T will be utilizing half of the possible heat and will be 50% efficient. So picture a water wheel that takes in water at the top of a waterfall but lets it only halfway down. So the efficiency of an ideal engine operating between two temperatures will be equal to the fraction of the temperature drop towards absolute zero that the heat undergoes. This turns out to be exactly correct, even though the reasoning behind it is based on an inaccurate model. The water wheel analogy proved to be useful in another way. Carnot knew that the most efficient water wheels were those that operated smoothly, with the water going into the buckets at the top of the same level, not falling into them through any old height and splashing around. In the idealized limit of a frictionless water wheel with gentle flow onto and off of the wheel, the machine would be reversible. If the wheel were run backwards, its power supplies from the outside, so it raises water back up. It will take the same power that the wheel was itself delivered in the normal operation. This idealized water wheel is clearly perfectly efficient, so the analogs of zero friction and gentle flow are what we need in the perfect engine. Getting the friction as low as possible is obviously necessary, but what exactly is gentle flow in the heat engine? For the water wheel, it meant having the water at the top flow smoothly into buckets that's at the same height, so no wasteful drop that would lose potential energy with no gain. For the heat engine, the analog is to have the heat flow from the heat supply into the engine with no drop in temperature. In a real engine, there must of course be a slight drop in temperature for the heat to flow at all, just as there is for real water in a water wheel, but this has to be minimized. So, as the heat is supplied and the gas expands, the temperature of the gas must stay at the same as that of the heat supply or the heat reservoir. The gas is expanding isothermally. Similarly, it must contract isothermally later in the cycle as it sheds heat. To figure out the efficiency, we would need to track the engine through a complete cycle, finding out how much work it does, how much heat is taken in from the fuel, and how much heat is dumped in getting ready for the next cycle. Watching this simulation gives the picture at this point. The cycle has 4 steps, and we're going to walk through these different steps. It has an isothermal expansion as heat is absorbed, followed by an adiabatic expansion, then an isothermal contraction as the heat is shed, and finally an adiabatic contraction to its original configuration. Now, you don't need to remember all those steps for the AP exam, but the cycle is represented in your text, and it's worth seeing it in action. And you can see this in action in this particular animation. We have an isothermal expansion followed by an adiabatic expansion, now an isothermal compression, and now an adiabatic compression. The isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. And you can see that the temperature changes during the adiabatic phases, but the temperature does not change during the isothermal phases.